Assalamualaikum. Bismillahirrahmanirrahim. Today I am going to discuss the Fourier series and Fourier transform in electric circuits. The Fourier series is of great importance in electrical engineering because uh, all the internal analysis of the devices is basically based on this Fourier series. You don't know, time domain doesn't give you enough detail to design the circuits. You need for the deeper analysis. For example, if you want to see the harmonics in your waveform, there is no way time domain can deal with it. You have to have the frequency analysis, which can only be done by the Fourier analysis. You already know that for the periodic signal, Fourier series has been employed, and for non-periodic or aperiodic signals, we have to use Fourier transform. Let's start. Suppose we have an input and there is a linear circuit and you have output. Similarly, if you have a sinusoidal inputs, then the your case is pretty simple, and you know that the Fourier series for the sinusoid is just two pulses uh, separated by a certain time on the opposite side, that is the odd function. And if you have a non-sinusoidal inputs, then what happens? What is the response of your circuit to that non-sinusoidal inputs? We will see for the non-sinusoidal inputs what will happen to the electric circuits. Actually, in that case, we need to discuss the components of that waveform. Okay, who is Fourier? It's a mathematician, and actually he developed a theory about the heat conduction, and also he developed some partial differential equation for the heat diffusion and solvent using some trigonometric functions. He is a evil genius, and he proposed the Fourier series in 1808 1807. What is the Fourier series exactly? A Fourier series, a periodic waveform, could be broken down into infinite series of simple sinusoids, which means when added together would construct the exact form of the original form. Actually, in simple words, any type of signals could be broken into a large number of infinite sinusoids, and when we are going to add them up, we will get the original function. Suppose we have a periodic function. You already know that the periodic function will be written like that: f of t is equal to f of t plus n of t. N is plus minus 1 plus minus 2. T is the period, the smallest value of t that satisfies the above equations. And this shows your periodic function. This is maybe you will get boring because it's just the mathematics, but to start with the circuits, first of all we need to know the theory of Fourier series, but it is exactly, you don't need to worry, just focus on the expressions. The expression for the Fourier series, just follow me. There is time signal. It will be broken into a E naught, that is the DC part or the average value of that signal, and the sum of cosine terms from n1 to n, and sum of cosine term with a certain coefficients, and these coefficients are real and called as Fourier trigonometric coefficients. And with the given value omega naught is equal to 2 pi over t, or you can write on in the alternative form like this way: c naught plus summation cn cos n omega naught t plus theta. Actually, these forms could alternatively, and these are the complex coefficients, and this is the simple thing to remember. It's a finite sum of harmonically related sinusoids. Now, 27. Explanation of the Fourier. And if we keep on moving, let's go to the next page. This is a complex form, and in its complex form, you can see that f of t is equal to c naught, that is the average value or the DC value of f of t. This signal is broken down into this one, and the next part, the summation. When we are going to break down the summation, what happens for n is equal to 1, the corresponding sinusoid becomes, this is n is equal to 1, c1 cos omega naught plus theta 1. This is the fundamental component, and if n is equal to k, the corresponding sinusoid is ck cos k omega naught, that is the kth harmonic term. Similarly, the omega naught is kind of the fundamental frequency, that is the frequency of the fundamental sinusoid, and the k omega naught is the k harmonic frequency. This is just the mathematics involved for the Fourier series, and the Fourier series actually is an accurate representation of periodic signal and consists of sum of sinusoids at the fundamental and the harmonic frequency. We already see this in the form of equations. It is an accurate representation, and as this notation denotes that n should be approaching to infinity, and the waveform depends on the amplitude and phase of every harmonic component. You can generate any non-sinusoid waveform by an accurate combination of the sinusoid function. This is pretty much important. Any kind of waveform can be generated from the sinusoid function. This is the key for the Fourier series. Any kind of periodic function can be constructed from the sinusoids. This is the property of the Fourier series, and some conditions. To describe the Fourier series, the waveform must satisfy the following mathematical properties. You can implement or you can apply in the Fourier series only to those functions which satisfy these four criteria. What is that? It's a single value function except at possibly a finite number of. At each point, it should have a single value. The integral of that function should be finite. Use over a certain period of time, if you are going to integrate, it should not be infinite. Your function should be finite, and it exists on each point with a single value, and it should have a finite number of discontinuities within the period t. Within a certain period, it should not have a large number of discontinuities, so it should have finite. Okay, and like the scale shape, it has within a certain period, it has a finite discontinuity like 1 or 2 at the edges of the scale. The finite number of maxima and minima within the time period. Okay, that's also understandable. In practice, FOP, VFT or ITB, this is the current or voltage function if above four conditions are satisfied. And if we recall the calculus, frequencies are integral multiple of some fundamental frequency form an orthogonal sets of functions. Surely, these two functions are orthogonal to each other. Okay. Over a series, if you integrate two orthogonalities together over a certain period of time, then it's sums up to 0, and there is some other conditions for this is these functions are important to solve some of the mathematics or mathematical form involved in the circuits. If you have a both sine, sine and cosine over a same sector over a same period, then they surely it is 0. And if sine both sines, then or both cosines, if n and m are same, then it is 0, and if they are not equal to 0, okay, then it is 1. Not same, then 0, sorry, go back. And if it is same and also not 0, then it is 1. So pretty interesting. And the Fourier coefficient, you already see there are some coefficient in the main formula, like here how we can calculate a naught, an, bn. Here is the solution for that problem. You know the average value. Average value, if you want to calculate the average number, average mass obtained by a class, what you will do, you add the numbers of the whole class divided by the total number of students. That's what we are doing over here. Over a certain period, we are summing up the function divided by the total time period. That is the average value. A naught, that is the DC value or the average value in terms of electrical circuit. This is the DC value, and in terms of mathematics, you can just say this is the DC value. And for trigonometric coefficients, the equation is little bit different. That is, you have to t by 2, and 2 goes up, and f of t cos n omega naught t, and n should be greater than 0. Similarly, Bn 2 by t, that is also t by 2, t naught integral d naught plus t, f of t sine n omega naught t. So these are very important. You don't need to memorize these. It's a pretty simple average value, and this is with the cosine, and this is with the sine function. Okay, to obtain a of k. Okay, if you have a kth, this is n 1, 2, 3. Then for the kth harmonic, what you will do actually, you have to evaluate the function at kth point. Okay, and this is your function, and it could be written like that. This is the plus, this is your obtain a of k. What you will do, this is the expression, then you can do this way. And actually maybe you will get confused by this, but you don't need to. It's a pretty simple. This is your term with the trigonometric components, and this is your average value. For the kth point, this function could be written like that. This is the total function. Okay, this is actually your function. This is your f of t. This is the average value for that function. Okay, pretty simple. And this is the trigonometric part. You already see. Okay, I will go back and let you know how it is written. Actually, your f of t is different now. It is a cos omega t. So when you are going to calculate these things, go next. This is it. Here you are actually plugging in the values of that a naught, f of t. You will plug in when you are going to calculate this average value. Thing he does, actually he directly put these. This is function directly put it over here. This comes from the formula. This thing comes from the formula. This is your f of t. Actually, this is your f of t, and this is for the average case. This is also only non-zero terms is for n is equal to k, and this only survives. This is just the interpretation how to find the coefficients. Okay, come back over here, then you will understand how it is going to work. Now you should be focused over here. This is a square wave generator, and determine the Fourier series and plot for n is equal to 7. Okay. It's pretty clear. First of all, you need to find the average value. Formula for the average value, you already know that. And this function is 1 from minus t by 2, t by 4 to t by. You can do it in either way. Okay, you have to take from, okay, take the full period, should be from minus t by 4 to 3t by 4 or minus t by 2 to t by 2, and this is total t. F of t, you know that this is 1 and it is 1 by 2. So the average value of this waveform is 1 over 2. If you focus a little bit, you already go through this Fourier series in some other course. I should keep moving. Okay, and this is the continuation of this example. Next is an even function exhibits symmetry around the vertical axis at t is equal to 0. So that ft is equal to f minus t. It's a very good. If you flip the function either way, if you rotate the function around this axis, the function remains the same. Okay, if you are going to flip, आप इसको उल्टा कर दें, सीधा कर दें, just rotate them around this 0, then the function value should not change. And actually this is an even function. For the even function, this bn is 0. Okay, the reason is that if you consider a sinusoid, if you consider the sinusoid and look at the sinusoid, if you are starting from the 0 and if go back on the negative side, it is from, and take the average value over that, then it is 0. Similar is the case over here. However, for the cos, since cos is maximum at 0, its value exists, and you will take the integral like that. This is from the formula 2 by t minus t by 4 over t by 4. You always remember, or you can just get from this formula, if you try to evaluate this function using these limits, this is always 0. Okay, if you try to put this minus t by 4, it always, for any number of n, it is 0. It didn't show up. That's, however, in this case, 2 by t minus t by 2, and you take the integral, and n omega naught comes out of the middle. And in the case of, in the case of integral, everything comes in the denominator. Okay, and evaluate it. Just put the values, and this is your final form. If n is an odd number, what will happen? This is 0. Put n 0, put n 2, will be cancelled out. and sine pi, sine minus pi is 0. And when n is odd, then we can generalize the formula. Then we can generalize the formula for the an, and where the value of q is n minus 1 over 2. It's just a generalization. You can write down any other form. So if you want to write down now this the Fourier series for this shape, and it is the average value a naught plus the function. This is 1 3, and this is odd up to n values. You just write down this one cos n. This comes from the formula. And if you okay, this is a1 a2, you can compute it by using the value a3 a5 a7. That's actually requirement. And if you plot this using the computer, you will get this kind of shape. Or if you just add them up, you will get this kind of shape. Look at the picture. If you are going to increase the number of harmonics, it will be the same as the original function, like that. So any kind of shape can be constructed from this. Let's keep moving. Now we know that the symmetry of the function, there are four types of symmetry: even function symmetry, odd function symmetry, half wave symmetry, and quarter wave symmetry. Even function, you already know that if you are going to flip, there is no difference. F of t or f of minus t, they are same. But for that, bn is equal to 0, as we see, and an is given by this function. Odd function, if you are going to flip, then it is the form of the function with the negative sign will come. Or if you are going to flip, then the slope is the other way around. And in this case, what happens? Your an is 0, an is 0, and bn has this kind of situation. Okay, let's keep moving. Half wave symmetry. For now, just you can Google it and see what is half wave symmetry. I couldn't go deeper into that due to the time constraint. In this case, uh, everything is given over a naught is 0 and a and bn is 0 for even values of n. This is a quarter wave symmetry, odd and quarter wave. Okay, this is also you can understand odd and quarter. This is actually for the graduate courses. We are restricted to even and odd symmetry here. Okay, let's even and quarter wave and odd and quarter wave. No, for even and quarter wave. Even and quarter wave, you have bn and an 0 for even values of n, and a naught is 0. And an is given for only the odd n. Now there is another example. Here we need to determine the Fourier series of this function. For it, just given time period is given, it's pi by 2, and you can calculate the omega from here. We already know that this is odd and quarter wave. Okay, from previous slides we know that a and bn for even value 0, and bn is given by that. That is the that's from that slide. It's just the repetition from that slide, and it only exists for the odd number. Actually, this comes from here. Okay. Now we just our function is we can write down the function f of m t by 4 f of m t by, and your f of t is 32 by 590. Actually, we are going to define the function over a certain period of time. Okay, and this f is 4 5 by 2, and actually if you are given with a certain slope like that, slope is you have a slope. Okay, you have a slope for this thing. This is it. Okay, you may have learned how to write down the function for this kind of waveform. 0 to t by 4, and you can finally come up with this one by using the values given, and this is a pretty simple formula. This is your f of t, and this is the common formula, and you will have a value of bn from here. An is 0, and bn you can compute it using that function. Actually, most tricky part is how to compute this thing. This is just a simple mathematics. It's I will leave this up to you guys. If you have a problem, then you can let me know. I will let you know how it's just simple mathematics. Now the Fourier series for that function only exists for the odd numbers, and this is your a naught is 0, and we just plug in these values over the main formula, and you have this situation. And you need a 7 terms up to 7. You can just 1 3, this is 1 3 for 9, 5 for 25, and 7 for 20. And similarly, you can also estimate the magnitude you have having for the next harmonic. It's extremely small magnitude, and therefore first 4 terms is enough to for the desired approximation. You can simply construct your function. If you are going to plot this way, you are going to sum up this waveform, okay, uh, using the computer, you will get the original waveform. This is the other waveform. For now, I am going to skip this part, and for the future, this is actually the complex function, and for now we will stick to this until this example. Thank you very much.